It's my pleasure to give a talk on one of our team's recent projects. The title of this talk is Streaming Dimensional Models from 3NF Deltas in Real Time. Now, before I talk about the architecture and the system, let me explain what is the business need that we're trying to address and what is our solution. Now imagine in a typical big company, after one or two product iterations, you're bound to end up with a couple of reference systems. Maybe you have a customer database, and in our case, we have a provider directory. And what we want is we want all dependent systems to always get access to the latest and greatest data. Now that sounds simple, but when you have a lot of data, it gets very complicated. You may be thinking, well, maybe we could do replication, we could do custom ETL. But in Quintiles IMS, we are big in terms of data. We are big in the healthcare space, so we have a lot of data about production, drug production. And in terms of reference data, we have many, many of those. We have different business units hosting reference data in different countries around the globe. So imagine if you want to pull a piece of data, you have to find that piece of data, connect to the database, and pull it. And in such a data-rich environment, just doing that selective data selection from a source is not simple. Now, imagine you're in Walgreens, and you want to refill your pharmacy prescription. The first thing the farm tech is going to do is try to pull your prescription and pull the provider and try to get the renewal for your drug. And the thing he needed at that moment is the doctor's phone number. And imagine that data was synced up a week ago. At that moment, stale data is just as good as no data. So we want to solve that problem for our business units. Make that data show up when you need it, just in-time delivery of this data. Now, as I mentioned, a custom ETL may work, but we have systems spread across different infrastructures, different firewalls. And in this platform, what we want to do is build a system that can send this dimensional data, denormalized data of your choosing, to your database in near real time. In short, what happens is when the data change in a source system, we want to change data, the denormalized data, in your database when that happens. And think of the convenience, right? You don't have to do a join. You go to your target database, and the updated provider information is in the system. Now, what you see is the architecture of our platform. I'm going to talk about the core components, which is really inside this Akka rectangle, and then I'm going to talk about the different technology choices. Our system has 5 major components. On the bottom left, in the Akka window, we have the statistic handler. Its main responsibility is to collect all the statistics from all the different modules and push it into Elastic. The second module is the subscription manager REST API. Now, since it's REST API, it really is the portal into configuring our system. And then we have the subscription manager. Its job is to go to Kafka and listen in on this change that just happened in the source system. And I'll talk about how does this delta get generated. And I'll cover that a little bit. The next system is the schema cacher. This is, I guess, the most complex piece of a system. What it has to do is figure out when a single table record change in a normalized schema, you have X number of tables, one record change. Now, how many different tables do I need to pull to give you that dimension? It has to figure out, create the join that's needed, and push it down and deliver that record. And finally is the assembler that makes use of that model, pull the actual data, and send that record that's relevant to the change that just happened in the source system. So I'll give an example, and it'll be more apparent. On the technology side, I mentioned Elastic up top for reporting. We have Akka, and my team has only been doing Scala Akka for about a year. And we have truly embraced this new technology and the Akka HTTP and the Akka actor system. And we can focus on the business rule and not on the concurrency, not on the low level, working in the low level logic. And we have Mesosphere for the deployment. On the right side, we have a HiveDB storing all of the deltas, all of the data that happened from the source system. And then finally, we have a message bus. Kafka has become a predominant messaging bus for Quintiles IMS. All of the big data asset movements all happens through Kafka. And one of the really cool features of Kafka, unlike other JMS type system where you deliver a message, it gets consumed by one consumer. In Kafka, you can set up a consumer group that allows you to listen in. You can process this message, and so can I, and we're not interfering with each other. And that's a key feature that allows us to build on top of this system. Now, I mentioned several times that we need to detect this delta that happened from the source system. When something happens, something has to stream out and tell us, yes, this record changed. But how do we get that? So where's my delta? In this slide, I'm going to present this very simple yet elegant solution that helps us to track down and report these delta changes from your reference system. And you probably guessed it because on the screen you see trigger and I'm like, yeah, that's right. This system will rely on triggers. So when something happens on a source system, if an insert happens, you get a single message that streams out into Kafka and eventually land in a data lake. In this case, the target DB is just a connection to our data lake where we deposit that change. If an update happens, we pick up this update record, we route it to the Kafka, and again, it lands in the data lake. So given this infrastructure is in place, in fact, this process is already being deployed in production to track all of the reference data changes. Because this is already in production, what we're able to build is a system that only has to listen in on the delta. This process is already taken care of. Now for the next slide, I'm going to talk about how we handle this delta message. One thing I've not mentioned is the messages are coming in as Avro messages. Schema on read property makes these messages easy to decipher. Imagine another system, one to listen in and process these messages. You could just look at the message, figure out what object, what table, what column, easily extract the content from this Avro message. So Avro is a really convenient format when you're moving stuff in and out of a message bus. Now from the top, you can see a message comes in and lands in Kafka. What I have not displayed on screen is some other process already picked it up and persisted onto the GDM DB. GDM stands for Global Data Model, is our naming, basically a centralized storage for this particular reference system, right? Right next to it is the reference schema that describes what the normalized schema looks like. And I'll explain a little bit why that's important. Now going back to the workflow, when the message comes in, a subscription manager, which is an actor-based system, and asynchronously, it picks up this message, and immediately it fires back a new topic and sends it to the next module. And notice the arrows. It goes out of Kafka into our actor system, and it backs into Kafka. So Kafka has become our buffer. We don't have to worry about losing messages. Of course, we could have solved it using Akka persistence, but it would mean that we would have to create another store to persist all the messages. The benefit of using Kafka to buffer these messages, Kafka has a setting that allows you to manually commit each and every read. When you read a message off Kafka, if you don't commit it, it's not consumed. Right? Just the mere fact pulling off doesn't mean I process the message. As the actor system is processing the message and it dies, whatever reason, When the actual system reboots itself, it will pull the message, and it will ask if that message was never touched. So you get fault tolerance, you get the buffering. There's no coupling between systems. So I guess this is your streaming model, your async model. So the cacher picks up this message, realizing that now it has to build the data model from Kafka. It goes to the reference system and pull all the foreign keys and build the data model. And in the next slide, I'll give a full example and explain some of the intricate details. And then once it builds the model, it sends this message back into Kafka again so that it can be processed by the assembler. Now, when the assembler is done, it pushes it back into Kafka. So I guess so far you get the pattern. We love Kafka. I mean, the whole process, Kafka in, Kafka out, Kafka in. This is a Kafka to Kafka pipeline that we built. And from my experience, the Kafka architecture has really enabled us to build a very reliable system. We have a 5 terabyte Kafka system, and we move billions of records, and not a hiccup. So if you're looking to really move volumes of data, definitely Kafka is a very good option. And let's look at the workflow as it relates to my Walgreens example, right? Our system, the model building is data-driven, and it's completely schema agnostic. How we build the data model is based on what information that's available about the normalized reference system. Imagine in the Walgreens scenario, the Walgreens app, in order to pull the address for any of your doctors in the database, it will have to at least hit 4 tables. So what needs to happen for our system to build the model for the Walgreens application is we need to pull the 4 tables, pull all of the foreign keys, and traverse this graph. So in fact, we use Scala graph to build this model. And I've used a lot of big words like Scala graph this, model this, but at the end of the day, it's basically a select statement that joins all of this table using the foreign key and primary keys and applying a where clause. Now on the left-hand side, you see in the provider address, that's the phone number that the Walgreens app, that's the only thing it cares about. It doesn't care about, let's say the data model has 1,000 other tables, don't care. Now, if the update event happened for the provider address, you're going to get one record in the Kafka message. It says, this provider address ID change. Now, what we need to do is join all of these tables, and the outcome is a single message that has not only the updated phone number, you're going to get the provider name, you're going to get the fax number, you're going to get the hospital the doctor worked in, you're going to get everything else related to that address change. And all the Walgreens app has to do is subscribe to this provider dim. That's the topic that will give you the updated just-in-time data delivery. So people have a misunderstanding about eventual consistency, and it doesn't mean that it will take hours or days to show up. So in the title, it says near real time. Our expectation is within 1 or 2 minutes. It will update a record, will show up in your database. How convenient, right? And this is not our actual schema. Our actual schema is way more complex. We have a scenario where we join 32 tables. Now, who wants to join 32 tables? So our system will handle the detection for 32 tables, and at the end of the day, you get one dimensional record that has content from all of the 32 tables. Yes, you have a lot of columns, but you can pick and choose. You don't have to worry that, oh, I needed this column and it's not in my view. Everything is taken care of. Now, on the integration side, earlier I mentioned we have a REST API. So to configure our system only has to care about what tables that we need to construct a model for. So our system does not care that how many people need the dimension. And that is a process that can be configured independently of our system. Now, what we have right here is we have a couple of simple APIs to add and remove topic. Everything coming into a system is a topic, right? This mirrors the Kafka model. Every channel is a topic. So all that we require for a system to function is you come into a system and tell us, yes, I want to know about the GDM loc. Well, you know, for Quintiles people, that stands for the global data model, the location table. And going back to our Walgreens example, I would make 4 REST API calls and alert this system that I want you to help me build a dimensional model for the 4 tables. So we would identify which of these instances of a system through the token, and then we would make 4 REST API calls, say add subscription, and then the system is fully configured, and it will build that provided dim whenever a record changes for any of the 4 tables. Now, for system that runs 24/7, you really need to be able to provide a lot of transparency into the system. Our system reports some of the key statistics that you really needed to know. For example, how many records are coming in, and how many are failing, and how many we're pushing out. And so on this chart, via Kibana, we're able to, it's already built in as part of a dashboard, that you can figure out the number of messages coming in through these different topics. Our GDM data model is about 1,000 tables. So you would, from a quick glance, you could see how many different kinds of updates are happening, right? Sometimes when you like to know, okay, how often are people changing this reference data? And here, you get a quick glance, and on the first 20, you get 400 or 500 messages. And if something is not correct, you could detect that why people changing certain tables, and you could easily spot problems. And of course, sometimes you just cannot build the data model for whatever reason. Let's say a column was renamed, the schema model for that reference table is out of sync. A column was renamed. So far, we just log the error and move on. Now, of course, we can add a retry, but for version 1, we just tell you this message cannot be processed. And finally, we report the number of dimensions we're able to build and able to push. So right here, we have 4 dimension models built and pushed out to Kafka. Now, in conclusion, like I said, this is a first big data project for my team, and we learned a lot. There was a lot of support from our East Coast team, and by the way, I'm based in the West Coast, so we had a good amount of training. But when you build a project, when you start a project from scratch, you learn a few things. And one lesson learned is don't go all in on a particular DB technology unless you have run a data proof of concept with some real data. Now that seems obvious, and what happened was we built a system with test data that we persist in an Oracle instance. When we're about to go into UAT, we switched to the real data sitting on Hive, and boy, performance was day and night. The Oracle was fast. It doesn't matter. We have a dirty table join. We're able to pull and filter. Bam, everything was fast. When we switched to Hive, Hive is a different beast. The partitions, the block size, the partition size, how many nodes, all those things determine how fast your Hive database will perform. It depends if you're going to use Impala to connect to that Hive DB or you use whatever else. So one mistake we did was we didn't test it real data on that real database or that particular database of choice. But of course, I think if we have started earlier, we would have been able to focus on performance tuning a little bit earlier. So we tuned way at the end, and I think that we lost some momentum there. The second lesson learned is distributed backend processes are hard to debug. So capture stats as part of your process output. We built the system, we had a lot of logs, but you have 4 or 5 modules, you have clusters, logs are spread across, and when you're trying to find that and correlate the stats, it's very difficult. So in fact, in the original design, we only had 4 modules. The statistic handler was added later on to aggregate and to add more stats where we need it. And so we could look at, is our system running fine? Did it hang? And we actually had a scenario where one of the actor thread was not able to connect to, I think it was Hive, or cannot connect. Somehow the thread pool was not able to grow and was static at X number of threads. And we could have never detected that. And of course, now I heard there's other, ops clarity and those modules. And if you have that, perfect. If you don't, build stats into the process. So design the system to be transparent from the get-go. And that'll save you a lot of pain in terms of debugging. And that concludes my talk. Any questions or comments?
Thank you for your talk. Can you hear me?
Yes.
Okay. You're working with deltas here, right?
Yes.
And you're building or updating your dimensions based on a stream from Kafka. How did you avoid data collision in your facts?
Can you stand a bit closer?
Sure. How did you avoid data collision in your facts in order to create your deltas to build your dimensions?
So the question is, how do I connect to the fact?
No, how did you avoid it, data collision? If you have more than one source in your facts, the different facts that actually have the same data that feed to the same dimension.
Okay, this
right?
delta is coming from a single normalized source.
All right.
So we don't have multiple competing. In a scenario like that, we would actually have multiple systems.
Mm-hmm.
This system is meant to take one reference system, normalize, and build models. So you would have to deploy. That's why with the token, you could say, well, this provider directory is for Europe, for Germany.
Right.
This directory is for London. So you have 2 different systems.
All right. Second and last question. How this process is better if you already have your full set of deltas to just apply the delta in bulk to your database instead of doing it streamed?
You mean to go into a Hive DB and stream directly all the delta to the consumer?
Right.
Well, you're still not getting away from having to join dirty tables, right? But without alerting, I think that's the real benefit is we're able to give you the data you need without you doing much work.
Right.
Now, if I stream in the delta, yes, I can, but I've not improved your user scenario by much.
Right, because in this
and
case...
that gives you a partial solution, but I think our solution gives you the luxury of not having to do any join, not having to know the data model. I think that's the benefit of our system.
Beautiful. Thank you.
Okay, thank you.
So I saw triggers in your diagram. So are you using the database triggers to stream the deltas?
Yes.
So, okay. So you ran into any issues creating triggers for a lot of tables? I don't know like how many tables you're talking about here. So when you say dimensions, it doesn't include the fact data. Is it only the dimensional data?
Right. So if this system was to deploy on the transaction system, it won't really work. Because imagine when it comes down, I'm going to join to this, whatever's on the Hive table, you're talking about hundreds and hundred million, it won't work. So these are for reference system, not fact table that contains gazillion amounts of data. Okay, thank you very much. Oh, okay.
Thanks for the talk. Basically, I have a question. You mentioned that you interact with Kafka a lot. So you basically publish every event and consume back to your Akka microservices. And I wonder if you, before designing the system, you considered using Akka or Kafka streams. And if you did, what was your... I mean, I understand the conclusion, but what drive you to using Akka with Kafka, not just Kafka streams?
So your question is, why did we choose to use Kafka instead of
Yeah.
Kafka streams?
And if you consider it at all using Kafka streams.
Or Kafka streams?
Yeah, Kafka.
I think the main reason is we have existing projects that have had good results with Kafka, and our DevOps team is comfortable. So we're using a pattern that has worked for us. I think that's the main reason. And I'm sure in our next iteration that we will consider a more streaming approach. Yeah.
Okay. And another question about actually joining. Can you please explain if you how is all this joining happening? Do you delegate it to the database as a join query, or you doing join somehow else?
Okay. So the question is, how do we build this join and where does it happen?
Right. Yeah.
The whole data model building process relies on the foreign key information in the Hive database. The join is actually built by using Scala graph. So what we get from the schema system is the foreign key relationships. Once you have the foreign key relationship, we can actually traverse and figure out how the tables are connected. And all of that is done in Akka and Scala graph.
Okay.
So there's no database, but at the last phase of the construction of the actual model, we will issue this joint statement, send it into the Hive database, and do basically a select with a where clause.
Oh, I see.
Because imagine if your Delta is on a particular provider, if you do a join without where clause, I'm going to pull all my providers, but when we apply the where clause, you're going to get one record that has the updated phone number and other information that's not in the original message.
Yeah, of course. Thank you.
Okay, thank you. Now I'm going to turn it over to JP Morgan.